Hello all, this is your Maverick here. Now we are going to discuss the important formulae and the concepts required to solve the numericals in the chapter Statistical Techniques. As of now, in Mumbai University, engineering students from computer, IT, AIDS, AIML, CSE, IoT, cybersecurity, and related departments learn this chapter Statistical Techniques in their semester 3, Engineering Mathematics 3. Whereas students from EXTC, ECS, Electrical, Electronics, Instrumentation, Mechanical, Mechatronics, Civil, Chemical, Automobile, and all other departments learn this chapter in semester 4, Engineering Mathematics 4. In end semester exam, this chapter is asked for 19 or 20 marks. If it is for 19 marks, there will be a question for compulsory section for 5 marks. Then there will be a 6-mark question and an 8-mark question. If it is asked for 20 marks, there will be two 6 marks question in different sets and an 8 marks question. This is the first part of the discussion of formulae and concepts, which will be followed by one more part. In this, we'll discuss what is mean, variance, standard deviation, covariance, and correlation. So let's begin now. First is the mean. It is simply the average. It's also known as arithmetic mean. Mean of x is denoted by x bar and is calculated by summation of all the observations in x divided by total number of observations in x, that is n. Similarly, mean of y, that is y bar, is calculated by adding up all the observations in y upon the number of observations in y. Next is we have variance. Variance is the mean of squares of differences, or say deviations from the mean. First is that we calculate the differences or deviation from the mean. For x, the deviation from the mean will be x minus x bar. So for each data point or observations in x, we calculate x minus x bar, then we square it, then we take the mean of all these squares. That's the variance. So let's write the expression and formula. So variance of x is denoted as sigma square x and written as x minus x bar the whole square by n. Now this summation of x minus x bar the whole square can be evaluated using the identity a minus b the whole square. So using that we get x square minus 2 times x bar plus x bar square. Before that, from here we can write the expression of summation x as n into x bar. Similarly, summation of y will be n into y bar. We also know that summation of 1 is n. Simply if we add 1 for 5 times, we get 5. Likewise, if we add 3 for 5 times, we get 3 times 5, that is 15. So we can even write summation of k will be k into n. So this will be summation of x square. We'll take the constant outside to x bar times summation x plus x bar square, and it will be summation of 1. So let's substitute the values we know. Summation of x square minus 2x bar times summation of x is nx bar plus x bar square Summation of 1 is n. So this is nothing but summation of x square minus 2n times x bar square plus nx bar square. If we simplify this, we simply get summation of x square minus nx bar square the whole upon n. It is not mandatory for us to know the proofs. If you just know the formula, it is more than sufficient. This is how we also say that variance is nothing but expectation of x squared minus expectation of x the whole square. Expectation simply means mean. So here we take the mean of x square, and also x bar denotes mean of x. So mean of x the whole square. So in similar lines we write variance of y as sigma square y, which is nothing but summation of y minus y bar the whole square, and summation of y square minus ny bar square the whole divided by n, or mean of y square minus mean of y the whole square, which is expectation of y square minus expectation of y the whole square. Standard deviation is the square root of variance. Now, why do we need to calculate the square root of variance? Suppose there's a data set of height of 100 children measured in centimeter. Mean of the heights is reported in the same unit, that is in centimeter. But when it comes to variance, it has the squared unit, that is, it will be reported in centimeter square because we take the mean of the squares of the differences. Hence, to bring it back to the same unit, we take the square root. Also, we use the standard deviation for normalization purposes also in uh, correlation, in normal distribution, and so on. So standard deviation of x is denoted by sigma of x, be calculated as square root of variance of x. So it will be square root of summation x minus x bar the whole square by n, which is equal to square root of summation x square minus n times x bar square by n, which is square root of summation x square by n minus x bar square, which is square root of expectation of x square minus expectation of x the whole square. Similarly, standard deviation of y is calculated as square root of variance of y, that is square root of summation y minus y bar the whole square by n, square root of summation y square minus n times y bar square the whole by n, that is summation of y square by n minus y bar square, which is the square root of expectation of y square minus expectation of y the whole square. Next we move on to covariance. Mean, variance, standard deviation, all these speak about the observations in only one variable. But whereas covariance tries to know the association between two variables in a data set. Basically, covariance is the mean of product of differences or deviations from the means of a bivariate dataset. So we calculate the deviation from x, deviation from y, multiply, add them, and divide by the number of observations. So yeah, covariance of x comma y is summation of x minus x bar times y minus y bar the whole by n. The summation x minus x bar y minus y bar can be opened up as x y minus xy bar minus x bar y plus x bar y bar, which can be simplified further as summation xy minus y bar summation x minus x bar summation y plus x bar y bar summation 1, which is nothing but summation xy minus y bar and x bar minus x bar and y bar plus x bar y bar times n, because we know summation of x is nx bar, summation of y is ny bar, and summation of 1 is n. So this can be further simplified as summation of xy minus n times x bar y bar minus n times x bar y bar plus n times x bar y bar. This is nothing but summation of xy minus n times x bar y bar the whole by n, or summation of xy by n minus x bar y bar, which is equal to expectation of xy minus expectation of x into expectation of y. Next, we move into Carl Pearson's coefficient of correlation, or simply coefficient of correlation, denoted to my small r, is the normalized value of covariance. When I mean normalized value of covariance, I simply divide covariance by the respective standard deviations. Why do I need to do that? Covariance can simply say only the whether the data or the bivariate two variables are positively correlated or negatively correlated. To measure the strength of correlation, we just simply divide the covariance by the standard deviations to get the value between -1 to 1, and then we do the further analysis. So R, which is the Carl Pearson's coefficient of correlation, also denoted by rho of xy, is covariance of xy divided by standard deviation of x into standard deviation of y. Nothing but summation of x minus x bar times y minus y bar the whole upon square root of summation x minus x bar the whole square summation y minus y bar the whole square. This is nothing but summation of xy minus n x bar y bar upon root of summation x square minus nx bar square into summation y square minus ny bar square. When I multiply n, I get one more expression, n times summation xy minus summation x into summation y the whole divided by root of n times summation x square minus summation x the whole square root of n times summation y square minus summation of y the whole square. Limit of r, Carl Pearson's coefficient of correlation is from -1 to 1, both inclusive. R is equal to 1 shows that it is perfect strong correlation. R is equal to -1 shows perfect negative correlation. If the values are closer to +1, then there's a strong positive correlation. If the values are closer to -1, if the value of R is closer to -1, it shows strong negative correlation. If the value of R is 0, then there is no correlation. The variables are independent of each other. If the R value of R is closer to 0 but positive, then there is weak positive correlation. Again, if the value of R is closer to 0 but negative, then there is weak negative correlation. Carl Pearson's correlation of coefficient is independent of change of origin and change of phase. When I mean change of origin, the data points are shifted from one point to another point. Basically, when it comes to numbers, we just add a constant to all the coefficients or subtract a constant to all the observations, not coefficient, observations. When it comes to scaling, all the elements are multiple, all the observations are multiplied by a factor, or all the observations are divided by a factor. So when we just change the origin or change the scale, so the value of R still remains the same. We'll illustrate this by an example. Spearman's rank correlation coefficient. It is denoted by capital R. When ranks are not repeated, we know that correction factor is equal to 0. Hence, R will be equal to, capital R will be equal to 1 minus 6 times summation d square upon n cubed minus n, where d is the difference between the ranks. When ranks are repeated, R is equal to 1 minus 6 times summation d square plus correction factor, the whole upon n cube minus n. Remind you that this 1 minus is outside the fraction. Now, how do we calculate the correction factor? Correction factor is 1 upon 12 times summation mi cube minus mi, where mi is the count or frequency of the repeated rank or the repeated observation. I repeat, mi is the count or frequency of the repeated rank or observation. It should not be the same as repeated rank or observation. It is the count or the frequency. Limits of Spearman's rank correlation coefficient is from -1 to 1, both inclusive. Whenever the term Spearman or rank is given, then only evaluate it. Else, correlation or coefficient of correlation simply means Carl Pearson's correlation of coefficient, small r. Thank you.